Hey guys, welcome back to Recreational Sniper, and you're watching the third episode of Firing Solution Friday. So in today's video, we're going to go over a firing solution for a shot, the last shot we did on the pipeline, which was 533 yards. We were at our shooting from an elevation of 1,672 feet, and our target elevation was 1,514 feet. Our horizontal range, actual horizontal range, is 533 yards, and our true range is 535.6 yards based on the angle we were shooting downhill. Your actual bullet drop based on how the distance that gravity is actually affecting the bullet is going to be your actual horizontal range at 533 yards. And then as far as all the other factors like your spin drift and stuff like that, or your Coriolis effect and all those things would be calculated for 535.6 yards because it's actually traveling that far through the atmosphere. Okay, so, and you know, the same thing with like when you do your temperature conversions and barometric pressure conversions, you'll want to do that for the true range, the actual distance from the muzzle of the gun to the target. But for most part, the majority of your bullet drop and everything like that is going to be factored in depending on your actual horizontal range, which is the range that gravity is actually affecting the bullet. So as we take a look at this first image, this is a top-down shot, an aerial view. I took a screenshot using Google Maps to get this image, and then I edited it and all that stuff. So when it comes to planning these shots and actually, you know, planning everything out, I'm actually, most of the time we go and shoot, I pre-plan all the math and stuff. So when we get there, we're not having to go through all that process actually after we've set everything up. We're not having to sit there and do a bunch of math and stuff. So I pre-plan most things. The only thing that I can't plan for is the exact temperature and barometric pressure that we're actually going to read when we get there, because on different days you're going to have different temperatures and different barometric pressures depending on if there's like a storm coming in or a storm leaving and that sort of thing. But I like to pre-plan as much as possible, so I do utilize Google Earth and Google Maps a lot for that, and it's a really good resource. In this second image we're actually looking at kind of a perspective view that will give you the idea of how the terrain actually lays of where we're shooting at. And we are shooting over a little bit of a valley there, and I just wanted to let you guys take a look at that, and so you can actually kind of see what's going on. The next image we're going to get into is going to be how we calculate our angle of fire, and I'll show you that it's actually a pretty cool thing. Is the calculator I'm using in my phone is Omni Calculator, and if you download that app and then you go and you search for right angle trigonometry calculator, it will allow you to change values, and you can input certain values for each leg of the triangle, and also also the angles of the triangle. But for the most part, we're shooting like you want to be able to input your elevation difference between you and the target, and then either your true range or your actual horizontal range. Your actual horizontal range would be that flat line across the bottom of that right triangle, and your true range will be the hypotenuse between you and the target. So if you're shooting like really steep extreme angles, this little calculator would be helpful for giving you the difference between your true range and your actual horizontal range. You can also calculate that out on your own if you know your angle of fire. If you've got like an angle cosine indicator and that sort of thing, is a tool that will allow you to do some math, and then you can from there calculate your actual horizontal range based off your true range. Now, the reason why we're talking about actual horizontal range and true range is because your rangefinder, if you don't know how it's set up, at least these newer ones, you can either set it to give you the true range, which is from the rangefinder to the target straight line, or you can get, they have these sensors inside nowadays that if you are aiming your rangefinder downhill or uphill, it actually has gyroscopic sensors in there that will actually tell it what angle you're shooting your laser rangefinder at, and it will give you it will calculate on its own and give you your actual horizontal range, so that you don't actually have to calculate for it. But you want to be careful, because you want to make sure that you actually have it set in, go into the settings, actually have it set to the way you want it. Me personally, I've already got my rangefinder set up to give me my actual horizontal range. And it just makes things easier, and it cuts out a little bit of math when I'm trying to come up with firing solution. So now let's move on to actually calculating this firing solution out. Alright, so I've said before, if you're shooting 1,000 yards or further, it probably is a good idea to go ahead and calculate your Coriolis, your horizontal and vertical Coriolis. But 1,000 yards and in, I would say you don't have to worry about Coriolis at all. It's so small of a change, so small of an effect at that range or less, that you really shouldn't have to worry about it at all. And then I would say your spin drift, you should probably calculate spin drift if you're shooting more than 400 yards. So between 400 and 1,000 yards, you're definitely still going to need spin drift calculation, but you don't have to mess with any Coriolis calculation. So, all right, let's get into this math problem real quick. All right, so first things first, we got to establish our variables, okay? So in this Firing Solution Friday, we are shooting 533 yards on the pipeline, but we're in a different position than we normally shoot at on that pipeline, and so therefore we have different altitudes. We've got different altitude of where we're shooting from, and we got a different altitude of where we're shooting to. So different final firing position and a different target area. So but we are shooting 308s in this shoot, so the FFP, final firing position, where we're shooting from, the altitude is 1,672 feet, and our target is at 1,514 feet, which is a difference of, I believe, 158 feet. So as you saw in that image before, I used the 158 foot elevation difference, and then it was pretty easy to calculate out the actual horizontal range from the true range. But like I said, if you've got your rangefinder and you know that it's set up correctly to go ahead and just give you the actual horizontal range, you won't need to actually do that part of the calculation, because it does it for you. So our actual horizontal range, AHR, is 533 yards. And alright, so let's get into this. So again, we're going to pick, what we're going to do here is we're going to take the chart that we have already set up for, we're going to take the chart that's under the altitude we're shooting at, and we're going to take the one that's above the altitude that we're shooting at, and then we're going to interpolate between those two charts and between the two different values that the charts give us, and then we're going to get calculate out from there the value that we need for the exact elevation that we are at. So at 28 inches of mercury, that's 1,910 feet in elevation in our area at 80 degrees Fahrenheit, which is about the temperature we were shooting on, because this is actually where this data comes from. And then at 29 degrees Fahrenheit, or 29 inches of mercury That's right at 899 feet in altitude. So we're shooting in between there. All right, so we're shooting at 1,672 feet. So first things first, we're going to look at the bullet drop for 500 yards and 600 yards because we're shooting in between 500 and 600 yards on here. And our charts are set up in 100-yard increments. So we're going to go out here at 500 yards and we're going to show that it's saying negative 3.7 mils. So obviously that means we're going to come up 3.7 mils. And then if we go to the 600 yard, it's going to say negative 5 mils. So if we were shooting 600 yards, we'd have to come up 5 mils. And then we're going to look at the other chart and find out that, you know, at this range, we're shooting, the difference in altitude really didn't matter that much or even at all, not enough to notice. And so at 500 yards, it's the same 3.7, and at 600, it's the same 5 mils. So it really didn't change. The altitude did not really affect the difference in bullet drop. Like barometric pressure at only shooting 533 yards or even up to 600 yards is not enough that even if we were at a difference of over 1,000 feet in elevation, it's not enough to actually change the bullet drop. So we don't really have to do anything with that there. But what we do have to do is figure out our bullet drop at 533 yards instead of 500 yards or 600 yards. So what we're going to do is we're going to do a little interpolation, and we're going to take 5, because 5 mils would be the drop at 600 yards, and we're going to subtract the mils at 500 yards, which would be 3.7, and we're going to get, what is that, 1.3, right? 1.3 mils. So this is where we actually need a calculator, unless you're just freaking awesome at maths. Anyways, unless you're just really good at it. So we're going to do 5 minus 3.7. I'm tired. I'm going to go ahead and make sure I'm doing this right. Okay, so we get 1.3, and then we are in between 500 and 600, we are 33 yards of a difference. So we're 33% of the way between this number and this number. Okay, and that sounds weird, but you know, it's 100 yards in between there, and we were 33 of those 100 yards difference is how far our target is off. So we're going to take that 33%, we're going to multiply it by 1.3, so times 0.33 for 33%, and we're going to get this crazy fraction here, but we're going to change it back to this. So we got 4.429, and then we're going to add that back to our 3.7 mils because we're shooting further than 500 yards, so it's going to drop more than 3.7 obviously. So 3.7, add that back on there, and we get another crazy fraction. And so it's telling us our drop for 533 yards is 4.129 mils, which we are going to round up to 4.13. So you've got an option here when you get a weird one like that. So you can only adjust in tenth of a mil increments, so either 4.1 or 4.2. It's closer to 4.1, and that's probably what I would go with out in the field. If you've got some different issues, like maybe it's a little colder or something, and the bullet's going to drop a little faster, the air's a little denser, you know, that sort of thing, you may want to go ahead and bump it up to 4.2, but that, you know, that just depends of how close the temperature is to your standard values that you're doing this calculation off of. See, we're using 80 degrees, and it was about 80 degrees when we were shooting that day, so it worked out pretty good. Next, we are going to look at calculating spin drift. Now, I would say Under 400, under 500 yards, maybe you probably don't have to calculate for spin drift. It's not gonna matter that much unless you're trying to hit something really, really small. But we're gonna go ahead and do it anyways. It'll be the one calculation we do here. So we can look at our chart, and we can look at we'll look at the 29-inch one because it's the lowest in altitude. So we'll need to interpolate our time of flight for 500 and 600 yards, and then interpolate that for the difference in barometric pressure. So if we look at this, our 500 yard time of flight is 0.719, and our 600 yards 0.893 seconds, and that is for our 29-inch Mercury chart. So we're going to go 29 inches, we're going to go 500 at 0.719 and 600 at 0.893. Alright, and then we're going to look at our 28-inch of Mercury chart, and it's going to be a little different. The time of flight is going to be slightly different. And we're looking at 500 yards, it's at 0.715, and at 600 yards, it's at 0.887. So 28 inch, go 500 at 0.715, and at 600 it is 0.887. So you're like wondering why we have a shorter time of flight at 28 inches of mercury, and that's because of the difference in altitude does affect time of flight. There's less less air pressure, less atmospheric density, and therefore less resistance on the bullet, and the ballistic coefficient of the bullet is, it makes the bullet a little more efficient flying at a higher altitude. So 28 inches of mercury, like I said, is like 1,900 feet, and 29 inches of mercury is around 900 feet. So now we got to figure out for our actual, where we're trying to shoot at. So let's go ahead and do the interpolation for 533 yards for these two, and we'll check the difference on those. And I'll kind of explain why it's a little easier to go this route than a secondary route that we could have gone. So, all right, we got 0.893 minus 0.719 equals some crazy number, and then we're going to multiply that again by 0.33 equals another crazy number, and then I don't know why I keep having to hit this button here that changes it to a decimal. But so we're going to add this back to our short range, our 500 yard time of flight. So we're going to add that to 0.719, and we're going to get 0.77642. So we're just going to round that down and say it's 0.776. And then we're going to do the same thing for 28 inches of mercury for 533 yards. 0.887 minus 0.715. We're going to get this thing, and then we're going to multiply that by 0.33. And it's going to give us this number, which is that, and we're going to add that back to 0.715. Hit that again, and then on this one we get 0.77176, so we're going to round that up to 772. So 0.772. So as far as our altitude goes, we've only got a difference of what is that, 4/1000ths of 1 second. so like 4 milliseconds of difference. So what I would do is just kind of pick in between. It's really not far enough of a distance to really have to worry about getting that exact for your spindrift that far away. You're going to be so close with, you could go really with either one of those numbers and it's going to be pretty dang close. The other way of calculating that would be to actually calculate your barometric pressure based on your altitude, which again, you could do that and you could use Omni Calculator. Actually has a air pressure at altitude calculator in it. So if you know what the altitude or the air pressure is at sea level, you can then enter in where you're shooting at, and it will give you your actual barometric pressure. Or the best way to do that is to actually read the barometric pressure out in the field, and then say if it's like 28.23 or something, then you would do the same thing we kind of did for the 500 and 600 yard difference. You would go 0.23 in between and that sort of thing. So what I would do is I'd either go with 0.773 or 0.774 as far as doing it this way. So then we'd run our calculation for our spindrift real quick. But before we do that, we're going to, another important part of the spindrift, we've got to do our gyroscopic stability factor interpolation here. So at 28 inches of mercury, it's 2.22, and at 29 inches of mercury, it's at 2.13. Now, I do know when we were out there, we actually took barometric pressure reading, and we were reading 28.23. So I do know that. That's a little bit of information I actually didn't give y'all earlier. So basically, we're going to do the same kind of interpolation here. We're going to go 2.22 minus 2.13, and it's really just easier to do it this way. We're going to get a difference of 0.009, or sorry, 0.09, and we're going to multiply that by 0.23. Actually, we're not, because this is kind of weird, but you got to kind of do the reverse of this, and I believe in my last video I actually messed this part up. But we're going to actually do the difference, and that's going to be 0.77 is the difference, right? 100 minus 23 is 77. So times 0.77. We get 0.0693, and we're going to add that to our 2.13. And the reason why we're doing that is because you actually have a higher, you've got a higher gyroscopic stability factor at higher altitude than you do at lower altitude. So we have to kind of reverse this a little bit. So our corrected gyroscopic stability factor for 2823 or 1672 feet in our case is going to be 2.199. So we really could just round this off to 2.20. It's 2.1993. So we'll just round it off to 220. And now we got to do our calculation. So our spindrift calculation is one of those again. It's 1.25 times your gyroscopic stability factor 2.20 plus 1.2, and then we're going to multiply that by the time of flight, which was, we already determined, we decided we're going to go 0.774, so 0.774, and raised to the power of 1.83. And this will give us our spindrift in inches, okay, at the distance we're shooting. So 1.25 times 2.20 plus 1.2 times 0.774, raise it to the power of, am I hitting the right button for that? I think I am. 1.83. Okay, so it worked that time. And our gyroscopic spindrift on this, or the spindrift on our bullet at 533 yards at our altitude is going to be 2.659407493 inches. So we're going to round that to 2.66 inches. Now we got to convert that to mils because our scope adjustment is in mils, right? So 1 mil at 100 yards is 3.6 inches, right? So at 533 yards, we would multiply 3.6 times 5.33. Pretty cool. So 1 mil at 533 yards is going to be 19.188 inches. All right, but we're only drifting by 2.66, so we're going to take 2.66 divided by that 19.188, and that will equal our mils. So 2.66 divided by 2.66 divided by 19.188 equals 0.138 and a bunch of numbers, so 0.14 mils of spindrift. So again, you can only go 0.1 or 0.2, and you're right in the middle, so it's up to you if you want to adjust up 2 or over 2 clicks or just over 1 click for your spindrift at 533 yards. So our final firing solution is we need to come up 4.1 mils. And because our spindrift is to the right, because we've got a right hand twist barrel, that means we need to come left 0.1 mil. Or optional if you wanted to go ahead and make 2, or 0.2 mil. But that's up to you if you want to make that correction or not. Same thing with the vertical. We could come up, or it's close enough, you could come up another 1/10 of a mil if you wanted to. But that's it. That's for 533 yards shooting at our altitude, 672 feet at our actual horizontal range, 533 yards, and that's it. That's how it goes. It's a pretty simple calculation, seeing as how we're not shooting that far. The only thing that really matters is spindrift and our interpolating our elevation adjustment. So other than that, there could be a factor of wind, and wind is pretty easy to calculate, and the way we have our chart set up here is we set it for a 10 mile per hour full value wind, so it's coming 90 degrees towards us, like from either our 3 o'clock or our 9 o'clock. So, and then if it was coming from a different direction, we would just use our wind angle cosines, and also we would calculate that and factor in the actual wind speed. If it's not exactly 10 miles an hour, we can adjust for that. And the reason why we use a 10 mile an hour increment is so that everything's divisible by 10 or multipliable by 10, and it makes life so much easier. And then same thing with our target lead, and this has to do with the speed of the target. And again, it would be moving at 90 degrees across in front of us from left to right or right to left at 1 foot per second, because it's pretty easy to judge 1 foot per second. You can count and then guesstimate distance of how far your target has moved in 1 second or 10 seconds if you wanted to. And then it's pretty easy to redo the math there. But same thing, if your target was coming at you or going away from you at a different angle than 90 degrees left to right, then you would use a angle cosine again and just do the math there. So anyways, we don't shoot at moving targets. At least, we don't really intend to. We don't want to. That's just for practice and other things, just to practice the math, like, and that sort of stuff. So anyways, I want to thank you guys for watching, and I know this video is a little bit long, but it's a lot shorter than the last one, and I hope you guys learned something, and I hope that maybe you would want to like, share, and subscribe this video, and I will see you next time in the next video. Thanks for watching.